I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die.
All right, our speaker this evening is Fatima Abdurrahman. As of today, she is Doctor of Philosophy in Astronomy at UC Berkeley. She received her PhD today. Earlier, Dr. Abdurrahman earned 3 bachelor degrees at the University of Maryland, one in physics, one in astronomy, and one in Arabic studies. Fatima has authored or co-authored more than a dozen technical papers, mostly on adaptive optics for seeing through atmospheric distortion and microlensing for detection of individual black holes. These papers include Fatima's PhD thesis, hot off the presses, I think accepted just yesterday, entitled Black Holes, Finding Them, Building Instruments That Help You Look, and How Systemic Racism Can Prevent You from Doing Any of That. Please welcome a woman of diverse skills and knowledge, astrophysicist and Wonderfest Science Envoy, Dr. Fatima Abdurrahman.
So hello, everybody. Like Tucker said, my name is Fatima Abdurrahman. I'm just finishing my PhD at Berkeley Astronomy. And my thesis included a lot of different kinds of work. I did instrumentation, I did astronomy education, but this component of my doctoral work is in observation, astronomical observation, and specifically the detection of black holes. So to introduce that and to kind of contextualize it, I'm going to talk about gravitational lensing. So in this talk, there is going to be 3 main questions I try to answer. The first one is, what even is gravitational lensing, right? How does it work? Why does it happen? Why is gravitational lensing useful to us as astronomers rather than just an interesting, fun thing to learn about? And how do we use gravitational lensing to find black holes, which is what I do in my research. So I'm going to break this into sections kind of along those lines, starting with some just fundamentals so we're on the same page. And I'll be stopping periodically, like Tucker said, to take questions at the end of each part. So without further ado, let's get started with our fundamental physics. So before we even say anything, let's talk about what gravity is, right? So gravity is the natural phenomenon by which all things with mass or energy are brought towards one another. Everything in the universe is exhibiting a gravitational force on everything else in the universe. So right now you are simultaneously affecting all things in the universe with your mass and its gravitational influence and being affected by every particle out there, right? Which sounds very, beautiful and poetic and kind of dramatic because it doesn't seem like we're influenced by the gravity due to everything. But the reason for that is we're dominated by the gravity from the Earth, right? So it's interesting to look at what dictates the strength of gravitational force. It depends on 3 things: the mass of the object being affected, the mass of the affecting object, and the distance between the 2 objects, right? So if we wanted to increase the gravitational attraction of 2 things, you would either have to increase the mass involved or decrease the distance. So when we think of gravity, we're usually thinking of Earth's gravity because Earth is both extremely massive and right next to us. Stars are even more massive than the Earth, but they're very far away. You might be sitting on a chair, which is right next to you, but it's not very massive. So it's this combination of high mass and short distance that makes a particular gravitational influence significant. Continuing off of that, let's talk about something more dynamic, moving objects. So let's say we have this little ball over here, and it's traveling through space on this straight line. If it passes by an object with mass, that mass is going to gravitationally influence it, and the object's path will be deflected towards the big massive object it's passing. And similar to what we were just talking about, this angle of deflection becomes more emphasized if the object is more massive or if you're passing by more closely. And this is basically what an orbit is, right? A planet orbiting a star is basically traveling perpendicular, but then falling in and falling in and falling in and just continuing to fall infinitely, or for a very long time at least. So that's our basic physics prep before we get into everything. Any questions about just these kind of first ideas about gravity? Okay, I'm going to take that as no.
Well, Fatima, maybe I can ask a question because I've left my microphone on foolishly all this time. When the smaller object is passing by the more massive object, is it fair to assume that the more massive object is affected as well, perhaps tugged a little bit from its former position before the small object came by?
Of course. So just like we said, everything's pulling on everything. All these forces are acting symmetrically. But just like the fact that Earth is technically being gravitationally influenced by the people walking on it, it's not strong enough to move Earth in any significant way. So in this particular example, and kind of the examples we'll be working with as we continue, there will usually be like the dominant mass, which is a lot more massive than whatever it's interacting with. So we don't have to really worry about that small symmetry. But excellent question, Tucker. All right, so we'll continue on and start to answer the question, what is gravitational lensing? So we just said that gravity is the phenomenon by which all things with mass or energy are brought towards one another. And we were just talking about the mass, but what about the energy thing, right? So for our purposes today, energy is light, right? Which is true, if not slightly simplified. So let's pretend we have our little cosmological flashlight over here. And just like our example before, we're going to shine it in a straight line somewhere through space. And it's going to travel on its little way in that straight line. But if there is a big massive object next to it, and that mass has a gravitational influence, which all mass does, then the path of light coming out of that flashlight is going to be deflected very similarly to how an object would be deflected. And again, just like the last example, the more massive the object is, or the closer in the path comes, the stronger that angle of deflection. So both objects and light interact with gravity. They can both be influenced in the way they travel in the presence of massive objects. And that's kind of weird, right? Because mass and light seem like very different things. A ball or a planet seems like a very different thing than a beam of light. Why should they act the same way? Well, to understand why two very different things act the same way, it's important to look at how we kind of conceptualize gravity. So one way we like to think about it is that both light and matter will travel along whatever the shortest path in space-time is, and gravity bends space-time. So what do I mean by that? One way of understanding space-time, which is kind of metaphorically described as like the fabric of the universe, right? The material that we exist within. We can illustrate that fabric, that space-time grid here in this image with this just like mesh grid. Sometimes people do simulations in real life where you hold a big sheet and stretch it out. And as you drop objects onto the sheet, you'll see that the heavier the object is, the bigger a dip it makes in the sheet, right? And maybe the sheet is flat in some areas far away from any of the objects, but close into objects, there's a dramatic well. And the more massive that object is, the bigger the well, right? So this is our space-time with gravitational wells surrounding massive objects. Now, let's move a little object through here. It's going to come in from the bottom left corner. So if an object comes in through here and it just passes along without really interacting with any of the wells, it's just going to keep going in a straight line. It's not falling into the valleys created by these spheres here. Similar thing, let's bring back our cosmological flashlight. If we shine it in a position where it's not interacting with any of those wells, it's just passing over the smooth part, it's just going to go on its merry little way. But if we shift things a little, let's bring in another massive object from the bottom left corner. This time it's going to come in close to that yellow ball. and it's going to fall into that well, and because of it, it's going to turn, right? You could imagine if it falls in deep enough, it might keep spiraling down like a drain, basically like an orbit. Same thing if we shift our flashlight over a little bit, so it's going to come in towards that orange ball's well. You have a similar deflection because you're reacting to the same change of space-time. So it doesn't matter whether it's an object or a beam of light. The nature of space has changed in such a way because of gravity that the shortest path is now round. A straight line in dense space-time just looks like a curve. So this is the most intuitive way I'm familiar with for understanding why light and matter are both influenced by gravity in the same way. So hopefully that clarifies what people mean when they say black holes or massive objects or whatever bend space-time. This is what they mean.
I guess another more classical explanation might be that you can think of a beam of light like a series of bullets, like a machine gun that fires out these photons. And so these little particles, they get affected just like big particles. They get, attracted by big balls that they pass by, and so they turn around. So for people that have difficulties of seeing space-times and this great seeing, a reason why light is affected by gravity is very simple if you see them as a stream of bullets.
That's an interesting way of conceptualizing it. Yeah, the fun thing about stuff like gravity is since it's all so abstract and we need models to understand it, you can really conceptualize it different ways and get creative in the ways you understand something like bends in space-time, right? Whether it's a stretched out sheet or photon bullets. All right, so moving on. We can compare the way that light is deflected by a mass to the way we see light deflected in other contexts, like a prism or a lens. So everybody's probably seen in some form a prism deflecting the direction of light, maybe also causing a rainbow in the process. That's very similar to what's happening here, even though they're different mechanisms. The reason for the deflection is completely different. Glass and light interfaces is its own whole different concept. But the fact that you have light traveling in one direction and then it changes directions is the similarity that makes us name gravitational lensing, because it is effectively acting like a glass lens. Or not necessarily glass, but a lens. So this metaphor also kind of makes sense when we see how it works in terms of observations. So let's say you're an astronomer here at your little telescope at night, and you're trying to observe this star. Now the starlight from that star, some of it's going to go to your telescope, and the light that comes to your telescope is what lets you see that the star is there. But most of the light from the star is going to go in other directions. It's radiating symmetrically from all angles. And those light rays that aren't going towards your telescope are not going to show up in your images, right? Cool, let's clear that. And now let's throw an object with mass in between us and the star that we're looking at. Now, usually the light would have traveled in straight lines away from the star. But because there's an object in the middle there that has mass, which attracts light, the light is going to be deflected inwards, causing more light rays to reach the telescope, acting like a lens, focusing light inwards, bringing a lot of light into a small point. That is what's happening here. So we call this object in the middle, somebody came in for a second. So we call this object in the middle the lens. And typically the object in the background, whether it's a star or a galaxy or any other light source, is just the source. So this situation is gravitational lensing, most simply put. To see a little more dramatic of an example than this, this is a simulation, not actual data. But in this simulation, here in the center is a black hole. And off to the top right is a galaxy. And the galaxy is going to pass behind the black hole, or equivalently, the black hole is going to pass in front of the galaxy. And you're going to be able to see the effect of the lensing. And this is really cool because you get this whole big distortion and this really bright ring as it passes. So this is like a very, you would be very lucky to catch this on camera in real life. But this is a good visualization of what's going on. And something to realize here is that even though it kind of looks like the black hole is tearing up the galaxy, and we have that image in sci-fi of black holes just kind of ripping everything apart, the thing to remember is that the background object might be much, much, much farther away from the black hole than the black hole is to us, right? The two things that are interacting in the image aren't interacting physically, right? It's just that the light traveling from the background object interacts with the black hole on its way to us. And so we see it differently. It's not exactly an optical illusion, but it's something of an optical effect, right? You wouldn't see like this if you were standing on the other side of the galaxy. You have to be lined up just perfectly to see it. Okay, so on that note, we know gravitational lensing, what it is, and we know that it's kind of cool, but next we're going to talk about why it's useful. But before I go on, I wanted to see if there were any questions.
Yeah, so I think a point you should make is you haven't really explained the black hole. Black hole is not really a hole, it's actually something very, very massive. And
right,
so
I'm going to get to that later.
Thanks, Carlo. Fatima, can I ask a question too? Let's see, we've got one written here. Can you algorithmically reconstruct the original object that is being lensed?
Ooh, so a person could. That is not my area of research, and I'm going to go a little bit more into the detail, the distinction between what I do and that, but that is an area of gravitational lensing work, where you basically see, I'm going to show you later, but you see lensed images and you use that image to identify what the lens is. But I'll talk more about that in a little bit, as well as more about black holes.
Hugh Callie, thank you for the question. Fatima, maybe you'll put up with a question from me that asks something about history here, because I can imagine the laughter in some quarters when Einstein, 100 years ago or more, proposed that light is affected by gravity. Why did people believe that Einstein was right? I know he had quite a reputation by then, but still, it just seems unbelievable.
So this is actually very interesting because I feel like I could talk a lot more about this later, maybe. But I feel like a lot of gravitational lensing is often attributed to Einstein. And don't get me wrong, he did like make a lot, he developed relativity and that had implications about gravitational lensing, but there were actually people who theorized it before him. So there were at least two scientists who had predicted gravitational lensing before Einstein had written anything about it. And actually some scientists after the fact who probably made more significant contributions. But we tend to like focus on the part of the field that has something to do with Einstein because people like talking about Einstein. But anyways, point is, he wasn't the first one to bring it up. There was already some people looking into it. So I don't think it was the wildest thing, I guess, to imagine at the time.
All right, thank you.
Of course. Okay. Anything else? Let me catch up in my notes. Okay, so somebody had asked a question about reconstructing images, right? So this is actually perfect to segue into my next part. So one of the reasons that gravitational lensing is useful to astronomers is because it can be used as something of a cosmic scale, in that we can use it to determine the mass of things like galaxies in this case. So what we're looking at here is you can see these like blue, I don't think I can point with my cursor, but you can see the blue kind of circle, this fragmented circle around the center, right? These blue arcs in the middle third of the image, right? And all those blue arcs are copied images, basically, of the galaxy in the center of the image. Those are all lensed images, which you can create multiples of when you have complex lensing systems that are just that one galaxy or those two galaxies. And what is kind of harder to identify in the image is what the lens object is, right? So the galaxy is the background object and it's what we're seeing in the arcs. But the thing producing that is the cluster of stars in the foreground. So in one set of circumstances that is often studied, you have a galaxy in the background and a star cluster, a whole collection of stars in the foreground. And cumulatively, those stars, the collective gravity from those stars lenses the galaxy. And this type of lensing produces the most dramatic images of gravitational lensing that if you're familiar with it, that you've seen, or if you're not familiar with it, that you will see, where you have like these many repeated images and all this huge distortion. And so what people who do this kind of work do, basically analyze these kinds of images to measure the amount of distortion, how wide the image is, how many images there are, how the image is skewed, to determine what the mass of the cluster, which is doing the lensing, is. So remember, it's not that the background image is just the light, and it's the invisible thing in the foreground that is the actor in this case. So that's one area that gravitational lensing is useful. People use it to determine the masses of galaxies. And that's like macro lensing, we can call it. I work in what is called microlensing, which is a much smaller scale version of this phenomenon. We don't see dramatic arcs in our pictures. Instead, we see tiny changes in the brightnesses of stars that we observe over time. So let's make a little graph. We have this background star, the yellow star here. That's going to be our background source. And we have this little pink sphere off to the side. That's going to be the lens that passes by in the foreground. Now, we're going to pretend that every night we're taking our telescope out and looking at the star and measuring how bright that star is. And we're going to plot that over time. And as the lens moves in front, you can see that it gets brighter, because remember, all that light is being focused in. It's being magnified. And as the lens moves past it, it goes back down in a symmetric shape. The foreground lens, of course, will continue to move. It's not just going to pass in front and then stop forever. And as it moves on with the rest of its life, the background source stays where it used to be in terms of brightness, but it had this peak for a while. And this peak is what we call a microlensing event, that period of time in which a lineup is happening that's causing a background star to get bright. And anything can create this, right? The background could be a star, but the foreground could be a neutron star, it could be another star, it could be a brown dwarf, it could be a free floating exoplanet. Any object with mass can be a microlens. The more massive it is, the more bright the background source gets. But even something as small as a planet can produce a measurable microlensing signal. So with that, let's talk about why this is useful in my research.
Can I ask a question before that?
Sure.
If you have a very strong lens, then it may focus on a very short distance, but then behind the focal point, all the rays may go apart again. So is it possible that we have a very concentrated foreground lens in front of the background source, that the light beams will not actually come together and focus and bring more light in our telescope, but they may kind of cross and diffuse and scatter the light around? Can that be observed?
So that actually brings up a part of this that I've simplified, and that is the relative distances of the objects, right? So what you're describing is basically, are things going to be aligned along the line of sight in the right proportions? And obviously, there will be paths that cross that do not line up in terms of distance away from Earth that we will be able to see the lensing of. We just observe the instances where it happens to line up perfectly. Microlensing is inherently like a serendipitous type of thing to observe, because you don't really know when it's going to happen. You can't really predict where it's going to happen. And many close, similar opportunities happen, but don't align just right. So it's a very random occurrence that has to have just everything tuned perfectly, like you're describing. Otherwise, it wouldn't line up in that way.
Okay. Yeah. Thank you. Thank you. That's good.
Mm-hmm. Thank you for the question. So, why is microlensing useful to me? Most of astronomy, almost everything we know about the universe, is understood through light. We look at how bright things are, we look at what color their light is, we look at where the light is, we look at how those things change over time, and we use that information to determine how big the universe is, how old the galaxy is, what the weather on an exoplanet is like. all of this is determined by looking at light, right? There's a couple things that you can look at neutrinos for, and recently we have gravitational waves, but most of what we know about the universe comes from looking at photons, light particles. Microlensing is interesting because it allows us to understand things without seeing their light. Remember, the background source in a microlensing event has to produce some light to be lensed, but the object doing the lensing doesn't have to emit any light for us to know that it's there. It's acting as a lens, not a light source. So even if it's very, very dark or even invisible, we could know that it's there without having to see it. And that's very valuable considering light is basically our only means for knowing anything in most of astronomy. It kind of lets us bypass the need for photons, right? And that is very useful for looking at certain types of objects that are dark. So for example, an exoplanet, like a free floating planet going throughout the galaxy without a star, is a very, very, very dim object. They're very faint. They're very hard to see just in an image, but their microlensing signal as they pass in front of other stars is measurable. Similarly, you can detect neutron stars or white dwarfs by microlensing. And most importantly to me, you can use them to find black holes. In this next section, I'm going to talk about how I use microlensing to find black holes in my research. So, any questions before we move on?
Hi, I had one question. So I think you did mention it's kind of useful if you have darker objects causing the lensing. So if you have an object like the foreground lens, which is actually emitting light, and does it happen that that interacts with with the light that is being lensed? Like, if I mean the object causing. Sorry.
I think I understand what you mean.
Yeah.
I didn't want to cut you off, though. So just like, does the light of the object affect what you see?
Right.
That's a very astute question because it does. And that's actually a very complicating factor, but it ends up being helpful if you're trying to look for something that has no light. And I will talk a little bit more about that, but absolutely, when we look at microlensing events, we have to account for the fact that whatever is doing the lensing can be adding its own light. So basically what that would look like for example, I'll try to show you quickly here. So see how the graph here kind of starts at the bottom and then has a bump. You can kind of imagine the graph starting higher up, where you have the light from the background object and the light from the foreground object combined, creating like a baseline, and then you have a bump on the baseline. Does that make sense?
Yeah, that makes sense. Thank you so much.
You do have to mathematically account for, you actually also have to account for light of other objects nearby as well. So it's good to catch this. This is the kind of detective work that was important in my thesis.
Okay, thank you.
Okay. Any other questions? That was a really good one.
Can you determine the sort of gradient that the dark object is providing for you to be able to determine what it is?
What do you mean by gradient?
The gravity, the depth of the hole that the object is creating.
Yeah, so this curve over here. So this bump, this graph, basically, we call this graph a microlensing light curve. And there's a lot of information encoded in it. In this curve, it's mathematically described by the mass of the lens, the distance from the observer to the lens, the distance from the observer to the source, as well as a few other things like how close in space they pass by. The tricky thing is that it's degenerate, which means that you can't have one curve that directly tells you all those quantities exactly, because they can vary in different ways. So you have to kind of do a little bit of extra legwork and measure some other things if you want to pull those quantities apart and say, here's the mass, here's the distance, rather than just a relationship between those two. But yeah, that information is in there somewhere.
Thank you.
Of course. Good question. Great questions with this audience. Anything else? All right. So, oh,
Fatima,
Tucker, you look like you're talking, but you're muted.
I want to just read a question, if you don't mind, from Jim Lawson in the chat here. Jim asks, for things very far away, wouldn't you expect there would be very many objects passing in front and causing microlensing?
I think space is a lot more empty than you think. It's, even though, you know, when you look at the sky, especially a bright sky like the one in this background picture, it looks like there's so much going on. But with the amount that we have to be zoomed in order to see this, and you'll see it in some images I show later of actual data, there's just not a lot in the field. It's not very dense, especially at the distances in which we can measure microlensing. Basically, microlensing is going to only show up for things within our galaxy. For things very far away, you need the huge masses of a whole other galaxy in order to see any of the effects, like in the dramatic pictures from before. But with our own galaxy, the number of stars is definitely not infinite, and it's a lot sparser than you might think. And that's why we don't just have, I mean, there are a decent number of microlensing events a year. I'd say there's a few thousand that we measure every year, but they're not just like all over the place.
Thanks, Fatima.
Anything else? Okay, so what was the question? Searching for black holes with microlensing. How do we do that? What's all that? What's that about? So I'm going to rewind. Somebody had earlier said that I didn't say enough about black holes, and he was right. I'm going to talk more about black holes now. But before I explain what a black hole is, we need to talk about what escape velocity is. So actually, before I even put that up, why is it that if I throw a ball straight up, it doesn't leave the Earth's gravitational field, but if a rocket ship takes off, it can, right? Why do some things leave Earth and some things don't? The distinction is one of speed. And basically there's a limit, a speed limit, above which you will escape the Earth or whatever body you're on, and below which you won't, called the escape velocity. So this velocity is the minimum speed needed for an object to escape the gravitational influence of a massive body, for example, the Earth. You can imagine it by like throwing an object up and seeing it fall back down if that object is traveling below the escape velocity, or above the escape velocity, it travels in a line and keeps going and escapes, right? Escape velocity, the velocity at which you escape, very intuitive. On Earth's surface, the escape velocity is something like 10 meters per second. So, and the escape velocity varies depending on the size and the mass of the body that you're standing on. But if you really work on it, get your jump speed up to 10 meters per second, who knows? You might just jump right off the surface of the Earth. Okay, so what is a black hole? Now that we have that information of what an escape velocity is, I can use it to define a black hole. A black hole is a body whose gravitational influence is so strong that the escape velocity is greater than the speed of light. Now let's think about what that means. The speed of light is the universal speed limit. Nothing in the universe can travel faster than the speed of light in a vacuum. So if even light itself isn't traveling fast enough to escape the gravitational influence of this object, and as we learned earlier, gravity does pull on light, that means absolutely nothing can get away from this thing, right? Now that doesn't necessarily mean that it's just a vacuum, like a vacuum cleaner kind of vacuum, not the empty space kind of vacuum. That doesn't mean that it's a vacuum out in space sucking everything in. In fact, if the sun turned into a black hole of equal mass right now, we would continue going around it on our same path. It just means that once something is close in enough, once it's in that well, that gravitational well in the sheet earlier, then there's no going back. And with that, I'm going to show you a scientifically accurate image of a black hole. Are you ready? It's this next slide. Here we go. That's what a black hole would look like, because it is inherently non-luminous. By the very definition of what a black hole is, no light gets away from it, which means there is nothing to be seen, right? So theatrics aside, let's give some little context about what a black hole is and where they are. Black holes, at least the ones the type we're talking about, the stellar mass black holes, are born when very, very massive stars run out of fuel and then collapse in on themselves. There's something like 10 million black holes in the Milky Way. About 0.1% of all stars in our galaxy will become black holes. And most of those black holes that are created from stars have masses that range from the mass of the sun to maybe 100 times that. And those can exist alone, or they can exist with a partner in a binary system where you have a black hole and a star orbiting each other. You can also have supermassive black holes, which can weigh billions of times the mass of the sun, and these exist in the center of galaxies. I won't be talking about that today, even though I actually did do a little bit of research as an undergrad with supermassive black holes. So I'm mostly concerned about the black holes that are alone. And the reason for that is that we don't know where they are. So this plot is showing us basically all the black holes we know about. The y-axis along the left side is telling us the mass of the object in units of the sun's mass. So one sun mass, 2 sun masses, 5 sun masses, etc. And I'm going to step us through this figure. So the top 2 sets, the blue and the purple, are all the black holes we know about. And you'll notice that there's 2 sets, and those represent 2 different detection methods. The purple dots are black holes that we discover because they exist in binaries with stars. So when you have a black hole and a star orbiting each other, the black hole is going to suck in some of the material from the star and make it glow, and we can see that glow. So those purple dots are the black holes we know through that method. The blue dots on the top, those are LIGO black hole mergers. So when 2 black holes are in a binary together and they eventually merge or collide into each other, that action releases ripples through space-time that we can somehow measure. But that is the topic for a different talk. But I'm sure many of you have heard about the work LIGO has done in the past decade. So these blue sets of points, those are all the black hole LIGO mergers that we know about. So in both of those instances, it's black holes in binaries that we know, whether they're with another star or whether they're with another black hole. It's the fact that there's something to interact with that lets us find them. Along the bottom of this figure, the yellow points are neutron stars. And neutron stars are basically a black hole that didn't quite make it. It was a star that died, but didn't have quite enough mass to become a black hole. And you'll notice that there's a gap between about 2 solar masses and like 5 solar masses, this middle band where there's not really much populated in this figure. And the question that astronomers who study these types of black holes are wondering is there nothing in that gap because nothing exists there, or because we can't find it with the methods that we're using? As you can see from the fact that the black hole gravitational wave mergers, the blue points, are in a different area in mass than the purple points, that means that our ability to observe certain events depends on the masses of the objects in the events. So gravitational wave measuring right now is sensitive to very high masses. Black hole binary with star observations are very sensitive to that kind of medium mass. But maybe there are smaller black holes that neither of those detection methods are able to measure. Or there's some law of physics that prevents having black holes that are about 3 or 4 solar masses. So this is an active area of research. And basically the reason microlensing is interesting is because it could potentially allow us to measure any mass objects, right? As long as it was massive enough to produce a gravitational lensing signal, which any mass black hole is definitely massive enough to do. If a planet can do it, even the smallest black hole can do it. So that's the question. People are trying to figure out what ways we can measure, detect the theoretical lowest mass black holes that exist by themselves without binaries. And because there's nothing in the vicinity for that black hole to interact with, the only way we could possibly conceive of observing them is through microlensing. So that's what I do. this is a paper that I wrote that got published yesterday, actually, by pure coincidence. Everything is lining up with this talk somehow, in which I examined 2 microlensing events from the 90s, and I try to figure out whether the lenses in those events are black holes. So I'm gonna just really quickly show you a couple highlights from the paper and what some actual data looks like. So I studied 2 targets in this paper. This is only one of them. It's just easier to explain through one example. This is called Macho 96 Bulge 5. It was detected by the Macho survey in 1996. It was the 5th one detected in the bulge that year. That's where the name comes from. And what this figure is showing us is over the course of about 1,000 days on the x-axis, how bright that star is. More specifically, how many times its light has been magnified, right? So you can see at the very beginning, it's at 1 because it is its own brightness. But as that brightness is magnified, we increase to a peak and then come back down, right? And you can see different colored points that are coming from different observatories, because we have networks of observatories that do surveys to look for microlensing events, especially the short timescale ones where you need measurements every hour. You have different observatories at different longitudes that will keep continuous observation of it throughout the day, or day and night cycle, right? So this is one example of an event that I looked at. Cool.
Question: which of the curves, the white one or the red one, is the actual curve that you work with?
So both of those are models, and they're different because they account for different second order effects. The white curve takes into account the fact that there's a parallax contribution in the signal. So my example earlier, when an object passes in front of something in a straight line, well, I have it on this next slide. In my example, I have this go across in a straight line, right? But in reality, the Earth is moving back and forth, which means these things are wobbling back and forth. And because they're at different distances, they're wobbling back and forth in different amounts. So that wobbling produces the wiggles in the white curve, if you can kind of see. The red curve is perfectly symmetrical and has no wiggle because that's the parallax-free model. It's a simplification. But you have this kind of wiggle on the way up in the white curve because it's just accounting for more information. Good question. Yes, okay, so this is one of my events. This is the real data that they took back in the 90s in the Macho survey, and they published it and they studied it, and they couldn't determine at the time whether or not it was a black hole, even though the goal of this survey was to look for black holes, right? And the reason that they couldn't tell at the time is because it's kind of hard to see when the event is going on. So you can imagine when the event is happening, right? When you're at the magnified portion in time. If the foreground lens has light, but it's a small amount of light, then seeing it right next to the background star is kind of like trying to see a flashlight in a football stadium from an airplane, right? It's a small amount of light right next to a huge amount of light that's completely drowning it out in our images. So even if that foreground lens here is a brown dwarf, for example, which does illuminate a little bit, it would be completely impossible to see superimposed over a giant blue star or something. So the reason I study events that happened 20 years ago is because in the time since then, the foreground lens would have kept moving. And eventually, in all this time that's passed, it should have separated from the background source. So though at the time that it was happening, where the data that I showed you on the last page were being collected, you wouldn't have been able to see whether or not there was a luminous source. Now you should be able to, because now it's been 20 years, and by the nature of a microlensing event, the lens has to be moving, and it would have continued to move. So basically, what I'm trying to see in astronomical images that I took in the past few years, whether or not I can find a separated luminous lens. And the idea is that if I can't find it, then by process of elimination, it has to be a black hole. So let's look at some images. So this right here is an image of the background star taken by the Hubble Space Telescope in 1999. The very center point, so each of the blue blobs is a star. They're marked with a small orange ring. That means it's a star and not some artifact of the camera. And the one in the very center is the star that we were looking at a few slides ago that got bright, the one that got lensed. That's the background star. And this is 1999. The event was discovered in 1996. So it's still very close in terms of the timescales of this event to the peak. So if there is a lens, whether the lens is luminous or not, it's going to be right over top of the source right now. So the idea is, if we took a picture now, would there be anything new? In specific, is there anything new within that big orange circle? Because that big orange circle is the maximum distance that something could have reasonably traveled since then. And when we look at our new images, we find that though they are a lot higher resolution and prettier, there's nothing new within that area. There is the same one companion star that was there 20 years ago. It's in the same place. Nothing new has come up in that region of the image, or in any of the other images that we've taken in different areas of the electromagnetic spectrum at different wavelengths. So this is our first indication that the lens is a black hole. Because if the lens was a star or a planet or a brown dwarf or something, it would now be far away enough from that center blob that we would be able to see it. And yet there's nothing there. So what my paper is, besides what I've shown you so far, is me trying to think of every possible way we could have missed something and eliminating that possibility. Maybe checking if the lens moves so slowly that they're still overlapping, and examining the spectrum of the source, nothing there. Looking at different wavelengths and seeing if it exists in a different band, nothing there. From every perspective, and there are many perspectives I looked at if you want to look through that paper, there's no indication that there's any luminous object in that area that has shown up since this lensing event, which is strong evidence that for both this event and the other event that I was looking at, the lenses are in fact stellar mass black holes, which is exciting. Space, right? So I won't bore you with too much more technical stuff. Instead, I want to start summarizing here. We're right on schedule, actually. I wanted to end with 10 minutes left, right on time. All right, so what did we learn? Objects with mass change the way light travels by bending space-time. This is called gravitational lensing. If we observe a lensing event in progress, or after the fact sometimes, we can identify what caused it, maybe determine its mass, the distances involved. And this is really useful in trying to find invisible objects like black holes. So with that, I'll take any other questions you have, and thank you for coming out to listen to me today, talk about my science.
Thank you, Fatima. Yeah, you'll get a more serious round of applause here at the very end, I guess, because we want to see if you're really going to answer these tough questions so well.
Oh, of course. The questions are always my favorite.
Let's see. I'll try to hit a few of the chat questions that haven't come up yet. Stuart Newsom asks, have there been observations of this gravitational lensing phenomenon where there is no apparent source, like a black hole, etc.? Could such instances be due to dark matter? Maybe that's what he's most getting at.
So actually, we use black holes to measure dark matter. People do use lensing, gravitational lensing, to measure the mass of dark matter. So this is not my area, so I'll only try to speak to it very approximately. But to measure, for example, like the dark matter halo of galaxies, the type of lensing that I showed with the dramatic arc images, that large scale lensing, that can be used to measure the mass. If it's like a star cluster that has a dark matter halo that's doing the lensing, you can use that to measure the total mass. And then if you observe the stellar mass and subtract that off, then you have the dark matter mass. So yes, this actually is used with dark matter as well. Anything with mass can do lensing.
Fatima, Nellie asks a question about space-time itself. Is there a more tangible description of the space-time which is being bent? Has anyone described what is actually bent? Is this similar to the ether described historically?
So I feel like this is a very unsatisfying answer, but the most true understanding that I think one can have is purely mathematical. And I know that's not a satisfying answer, but I feel like that's just kind of the nature of this thing, where it's so abstract, right? It's so beyond the conception of like our human experiences that we only really can understand it through metaphor. The same way, you know, we conceptualize atoms as being like a bunch of little balls that are held together and moving around in orbits, but that's just a simplification we use to explain the things we see. It's, you know, we try to be as objective as possible, but ultimately we're still telling stories. And some stories hold better in some conditions, and some stories will give you more detail, but ultimately they're all stories. And the only place where it really stops being a story is in the pure mathematics of it. So the only place that I've personally found like a grounded understanding in like my sense of what space-time is and how it works is, as boring as it sounds, learning the math. I feel like that's like the lamest answer you can give for a question about the universe is go learn math, but it's a complicated thing to explain, you know, and a complicated thing to understand.
What is space-time? It's a killer.
Right. Yeah. I mean, even the idea of space-time so I'm a scientist, but I'm also a social scientist. So I do science and then deconstruct it, right? So even the idea of space-time is like a construction that we use to understand these things. And again, it's a story, and it's a story that matches up with the math to an extent, but all of that has limits. Even relativity has its limits, you know?
Fatima, Philip Cannon asks a question that I think you've answered in part. Does the wavelength of the light matter that's being microlensed? By taking the same image in different wavelengths, what can you learn?
So that's a very interesting question. And thinking back to earlier when I was talking about how gravitational deflection is very similar to optical deflection, right? We all know the image of a prism and the light goes through and bends and comes out a rainbow. And the reason that happens is because when you're talking about a glass prism, the angle of deflection is, among other things, dependent on the wavelength of light, which means that different wavelengths of light get deflected in different angles, which is why white light, all the colors in our visible rainbow, separate in like the Pink Floyd album cover, right? But gravitational lensing is actually an achromatic phenomenon, which means that it does not depend on the wavelength of the light. So the only thing that would change in different wavelength observations would basically have to do on what wavelength the background source was. So for example, if the background source emits in the infrared mostly, and you observe it in the ultraviolet, you're just not going to see anything. But if you observe it in the infrared, you will see the event happen. You won't see variation in the event at different wavelengths. It's kind of just whether or not you do see the event at that wavelength. But that's a great question. It's a very subtle thing to pick up on.
Two of your inquisitors, ask about MACHO, wondering if that stands for Massive Compact Halo Object, and how you first found the macho in the first place.
So this is actually a funny story. So dark matter has been a question for a long time that people have been trying to propose different. Sorry, I'm going to take a sip of my water because I'm coughing. Promise I don't have COVID.
Wonderfest and not Tam should just supply you with a bottle of water, but you've got your own. Great.
I'm good. The question was, I totally blanked.
Machos.
Okay, so dark matter. People wanted to know what dark matter is, and they had all these different hypotheses of what it was made out of, right? Like, is it particles? Is it objects? Like, what is it? One of the first ideas was that it was a new kind of particle that interacted gravitationally, but not electromagnetically, meaning it pulls on stuff, but doesn't glow, right? And they called these weakly interacting, so no electromagnetic radiation, massive particles, particles that have mass, weakly interacting massive particles, or WIMPs. And in response to this, another group of people trying to find dark matter proposed that, well, what about instead of being particles, it's actually large objects that just aren't very luminous, like a big collection of neutron stars or a big collection of black holes. And we can call that massive compact halo objects. Massive, because they have mass again. Compact objects are white dwarfs, neutron stars, and black holes, stellar remnants. So massive compact halo objects in the halos of galaxies. So massive compact halo object, MACHO. And it's a very specific, astronomers have a very specific like affection for acronyms and like clever acronyms and riffing with acronyms. So that's the deal with machos, unless you had a more specific question to ask about it. I'm not sure if I even answered the question, but they just named the survey after that. They were basically looking for black holes and neutron stars to see if it could account for the amount of dark matter we understood to be in the galaxy. As I understand it, that is not still a dominant theory.
But I think Philip is asking how you found your macho.
Oh, so I didn't discover it. It was detected in a survey back in 1996. So this survey was running in the 90s. And they published the event. So they observed the event and then they published that. And many people have studied it since then. A lot of kind of big events like this are repeatedly studied over time as more and more data come out. But I didn't like discover the event. I followed up the event, basically. I discovered it in a survey.
Right. And is it fair to say that neither WIMPs nor machos, however cleverly defined and acronymed, aren't a good explanation for the effects of dark matter?
I don't know. I feel my understanding of the nature of dark matter is that it's probably a kind of particle, right? Like, I think our understanding is that it's whether it's axions or WIMPs or something else. I think we think that it's a particle rather than massive, like compact objects or extended objects. So WIMPs might not be that far off, but it's a very active question of research. Like, honestly, we don't know what we understand what dark matter does. We don't know what it is, if that makes sense. Yeah. It's kind of like gravity. We understand how it works, but we don't really know why, right? At a certain level. So,
Jim Lilienthal asks, what will it take, and likely how long will it take, to get an estimation of the frequency of stellar mass black holes in the galaxy or the universe?
I think that'll be done within the next few years. Like, there's a couple other teams that are kind of doing the same research as me that are a lot more dedicated to it, that will continue working on it. And there are only more and more surveys coming out and more instruments that are being dedicated to this kind of work. And now that we understand very well how to make this measurement, it will probably be made within the next few years. And I would assume that after just a handful of measurements, we'd be able to start generating statistics about the frequency in the galaxy. So yeah, that is definitely in the kind of near future range, which isn't an answer you would often hear for questions of astronomical discovery timescales, I guess.
Fatima, Steve Moore asks a question that he thinks is rather basic. I hope everyone agrees, I'm not so sure. To determine distance and or mass of the object that is microlensing, do one of those properties, distance or mass, need to be known by other means, maybe parallax, in order to determine the other by lensing?
So here's the tricky thing. It's not just two variables that can change, where if you know one, then you definitely know the other. It's three. Object mass, the lens mass, sorry, lens distance, and source distance. So, and to a lesser extent, there are a couple other parameters that influence a little less, that are easier to determine from the light curve, but these three are the ones that are kind of really hard to disentangle. And even if you know one, for example, sometimes you can know the distance to the background source through parallax. These two are really hard to measure. And you do have to do something else to measure them. Parallax is one way. A few other ways. Oof, this is kind of complicated, but I'll try to explain it. I'm going to use my hands for gestures, so that if that is helpful. How do I explain this? Okay, so in all these figures here, we're imagining geometrically that the lens is a point, right? We're imagining that it's infinitely small and that the area of the lens on the sky isn't big enough to matter. And that's what gives us this shape. However, in reality, things have size. They're not infinitely small. And if the width, the size of the lens is big enough in relation to the other things in the system in the context of our images, then the curve shape changes. It's a pretty nuanced thing that you kind of have to get into math to explain why and look at caustics and stuff, which is kind of outside the scope of this talk. But the fact that it has size, and so it doesn't instantaneously pass an object and it crosses over it for some duration, makes the top of this peak flat. Because you're not instantaneously entering and exiting. You spend some period of time crossing in front of the star. So if you can measure that, which is possible to measure, it is done, then you can start to disentangle the mass of the lens from the distance to the lens, for example. That's one example. Another example is that in addition to the light becoming brighter, in addition to this magnification effect that microlensing has, there's also a positional shift that occurs. If you, I don't know that I have a slide that really, maybe this next slide after this kind of explains it. What am I trying to show? So you can see here, like, follow the top curved line, right? If that top curved line that went up and then comes back down comes into your telescope, then you're going to understand that point of light as being, you kind of have to imagine from the left point, drawing a line that follows it up and to the right. You'd basically see the star shifted from where it actually is, because since the light changed directions and your brain intuits a straight path, you kind of backtrack to straight and imagine or understand the star to be at a different point. And if you can actually measure that small shift in position that occurs because of this as the event happens, then you can also back out the mass of the lens. So there are different like small effects like this that are kind of hard to measure usually, that tease out that additional information. And I'm gonna slowly push through my slides again. Any other questions?
Yeah, Fatima, I see that Carlo has his hand raised, and I just want to say right now that I envy your students. You're giving great explanations. Carlo, please ask your question.
Please.
Yeah, I'm interested in those black holes between 1 and 5 solar masses, which you say it's kind of an open question whether they actually exist. So question number 1 is, people have done calculations of what holds a black hole together, and are those models not good enough to predict whether such black holes could exist? And the question that follows up is, are there models that would describe what we would see if such a black hole of, say, 2 solar masses actually coincides with a regular sun like ours? Would that give some special way of scattering the, the mass of the sun all over the place? And how would that look? Are we at the state where we can model these things so we can look then for the effects?
So this is an interesting thing, right? Because a lot of our understanding of stellar evolution, right? And it is stellar evolution that produces black holes, because it's one of the end states of a star. our models of stellar evolution are partially based in fundamental physics, right? We have an understanding of, for example, nuclear physics and radiation transfer and how all these things operate to a certain degree, right? But then they're also based in our observations of, for example, frequencies of different types of stars, right? We can observe that there are very, very, very many high mass stars, very few high mass stars and many more low mass stars. And that tells us something about the way stars form. And we can see that in certain contexts of different like chemical environments, it forms one way versus another. So our understanding of the process is very based in both theory and observation. When it comes to black holes, there's kind of this chicken and egg problem where we don't have the observations to back up a lot of our theories, right? And you can kind of show, you can make an argument mathematically that they're, so the hard line is that the mass limit between a neutron star and a black hole is about 2.14 solar masses.
Oh, I see.
Before that, it can be a neutron star, but past 2.14 solar masses, a neutron star collapses for sure, right? The question is, does it collapse into a black hole of that mass right above it? Or is there some process that we're not accounting for that makes it necessary that there has to be some kind of mass increase or something? So I think this research is going to help us answer that question.
So then I would like to formulate my second half of the question. Do we have a model what we would see if, say, a 2 solar mass neutron star passes through our sun? What would happen? What would we see?
Like, would it pass if it passed in front?
Yeah, it really collides with our sun.
That's just like straight up collides, like actually
a direct collision, yes.
I mean, I guess that would be like your LIGO merges, right? You have that the gravitational radiation that occurs from a collision of that type of scale.
But here, since we can actually see the sun, we definitely have a spectacular visual effect as well. And I was wondering whether somebody has tried to figure out what that would look like.
I don't know. I know people have done a lot of interesting visualizations when it comes to gravitational lensing and black holes and all this stuff. Like, for example, the movie Interstellar, if any of you have seen it, actually went to pretty extreme lengths to like calculate not only what a black hole, like wormhole, would look like theoretically, where you are lensing the location on the other side of the wormhole and projecting that image into another place. But they even like added the equations for what that image moving through an IMAX camera would look like. So people have definitely gone to extreme lengths to kind of create these, things that we probably won't observe. But as far as I know, I've not heard of somebody colliding something with the sun to see what that would look like, but it's interesting. You should try it.
Yep. Thank you very much.
Thank you for the question. Fatima, I realize I promised you just a 1-hour talk, and here you are beyond that time. Perhaps those who printed other questions will forgive us, but I want to first thank everybody for being here. You've been a great audience. I think Fatima will confirm that.
Great questions. Really good questions.
Remember that